Welcome. RQM Technologies introduces the first quantum framework that truly measures quantum properties at scale. Quantum mechanics has long needed a breakthrough in metrology that certifies quantum networks, timing, and sensors in operational conditions. RQM Technologies directly addresses this gap with Quaternionic Spectral Geometry, a unified mathematical framework built for a real deployment of quantum systems at scale. This is the first mathematical tool that makes scale-valid quantum metrology possible. By implementing Quaternionic Spectral Geometry, we reveal an operational picture that gives rise to Resonant Quantum Mechanics, a comprehensive understanding of quantum systems which can offer metrology for deterministic readouts anchored in quantum geometry. Let's dive into what this mathematical breakthrough means. Quantum mechanics traditionally works in Hilbert space. It is abstract, basis-dependent, powerful, but detached from geometry. Quaternionic spectral geometry represents quantum states in their true geometric space that quantum systems already live in. This means quantum states are no longer just mathematical symbols, but measurable points in a geometric landscape. On S cubed, or the quaternionic hypersphere, we can directly describe spin orientation and entanglement, capturing how qubits rotate and align. On the real number line, we can track resonance, drift, and stability in a way that measures how systems move across coherence over time. Together, this quaternionic spectral geometry reflects the actual geometry of quantum behavior, allowing metrology to describe systems as they really are, with orientation, resonance, and coherence inseparably linked. From this foundation, a new depiction of quantum mechanics emerges: resonant quantum mechanics. Current quantum systems are measured by device lifetimes such as T1, T2, and single device fidelities. Today's systems tell you how long a qubit keeps its energy and how long it keeps its phase, but evaluates a single operation to a single target metric. Though these numbers are useful in the lab for an isolated qubit, they do not survive the leap to larger systems. When you connect qubits into processors or link clocks and sensors into networks, these metrics collapse. Current systems cannot tell you how orientation errors spread, hold across modules, or how systems perform under real environmental noise, and even the best device fidelities give no guarantee once those devices are rotated, entangled, or deployed in the field. With resonant quantum mechanics, we can now do things that were never possible before. Anchor-generating quaternionic factorials, operating as an extension of the gamma function unveil resonance ladders, which create quantization wells where systems stably exist. In other words, discreteness isn't imposed. It emerges directly from hyperspherical geometry as a deterministic, measurable feature of quantum systems. This is the first structural explanation of quantization, and it is the mathematical leap that unlocks scale-valid metrology. With resonant quantum mechanics, we can now define metrology that scales cleanly from a single device to a full network without breaking along the way. We can establish universal calibration anchors that remain valid across orientation, scale, and environment. We can create composable performance measures, so system reliability is no longer a patchwork of isolated metrics, but a unified, predictable framework. This means we can build a complete metrology stack that works across every scale. At the device layer, for a single qubit, clock, or sensor, RQM provides direct measures of resonance stability and alignment, rather than just reporting local statistics. At the system layer, when devices are connected, their resonance measures combine predictably. This allows entire modules, processors, or sensor arrays to be evaluated as coherent systems, not just as isolated parts. At the field layer, anchors and calibration beacons extend into real deployments. Systems can be checked and verified in the field with confidence that results remain true to the original standard. For commercial applications, this means a new generation of quantum clocks, which use anchor-locked resonance to provide position, navigation, and timing in GPS-denied environments, enabling communication that is both orientation agnostic and intrinsically secure. And quantum sensors can operate as networks. All of these capabilities trace back to the single breakthrough: Quaternionic Spectral Geometry's resonance ladder and anchor, generating quaternionic factorial stability points. At the team's core is the principal investigator of Quaternionic Spectral Geometry, ensuring both continuity of vision and technical ability. The team brings extensive research and engineering experience in prototyping and experimentation, ensuring the right theory is applied to adaptive execution. Their expertise encompasses the foundational principles of resonant quantum mechanics, capable of integrating systems engineering, prototyping, and field validation. RQM Technologies is transforming the foundation of quantum mechanics, advancing quantum computing, communication, and timing into next-generation quantum architectures. Quaternionic Spectral Geometry is the breakthrough. Resonant Quantum Mechanics is the bridge. And deterministic metrology is the inflection point. With your partnership, RQM Technologies will deliver the first true operational framework for quantum metrology at scale.